We are back with another Savage video. Thanks to everyone liking, sharing, subscribing to the channel here. You guys are the real rock stars around this place. In this video, we're going to talk about what goes on in the background whenever you're actually mining. And it's going to help you have a fundamental understanding of what crypto mining is. And I'd like to talk a little bit more about the actual mining process because I feel like I missed a couple of important things yesterday and wanted to clarify, and it seems prudent to do so since this is a crypto mining channel after all. Many describe crypto mining as software and hardware that solve some form of complex mathematical equation, but that isn't true. It's not really an equation at all. I touched on this briefly yesterday by saying that the mining software runs a hash function, a one-way block hashing algorithm, on the block of new transactions along with previous block header, and that's closer to reality than saying it solves a complex mathematical equation. I'd like to expand on this a little bit with a little bit more detail. And what happens is the mining software that you run on a mining rig acts as a node or a dedicated computer on the network that searches for transactions that have yet to be validated. These transactions are considered in progress but not confirmed and are sitting in what's called the network's memory pool. The unconfirmed transactions are bundled into a block of transactions. The block contains some additional information such as version numbers, timestamps, current difficulty target, previous block hash values, transaction nonce, and a Merkle root hash for the transactions in that block. In Bitcoin, a nonce is a 32-bit or 8-byte field that miners use for their cryptographic guesswork. Miners then try to solve the block by combining the hash of the new block of transactions with their own random input data. The nonce or number only used once in cryptographic transactions described a moment ago, in an attempt to find the hash results that start with a certain number of zeros. We'll get into the nonce a little bit more whenever we're doing an example of how this works on a very slow motion example we'll cover in a few minutes. You might be wondering what's with the leading number of zeros and all that stuff. The number of leading zeros required to solve a block is based on the current network difficulty to maintain the specified block time. The difficulty represents how many hashes it should take to find the solution and solve the block. And you can see that here in this example here, Bitcoin block 667702. I think it has 19. Yeah, it has 19 leading zeros. And we'll get into why that's significant in a few minutes whenever we do the example, do a little exercise. And just know that that's the hash that was found below a certain target to confirm the transactions within block 667702. Now let's look at an example here. Bitcoin has a 10-minute block time. So the difficulty of the block, the number of hashes required to solve it, is what the difficulty represents, should take an average of 10 minutes. If a miner is the first to solve the block, that solved block transactions is then locked in and added to the blockchain forever immutable. And you can see here that the difficulty over time has increased drastically. And we're sitting right now at about 20 terahash for the difficulty. That means that on average 20 terahashes is what it will take to solve the block to come up with a number that has a leading 18 zeros or lower, right? So it could be 32 zeros or 30 zeros or whatever, but it's got to be lower than this number here based on the hash functions that we run through a block. And if this is kind of confusing and not making sense, I think it will at the end whenever we do the exercise. Just stick around, we'll get to that part and hopefully make it make sense. For all that work, the effort of solving the block, the miner is rewarded with the currency's block reward or block subsidy. You can see that in this transaction here. There's 6.25 BTC from the block reward given to the miner that solved the block. And you can see how this doesn't match because there's some fees included as well. I think, yeah, right here shows the fees that this block also earned. So you're looking at 6.25 plus 0.91, and that gets you around this number right here. So for solving this block, the miner or the pool of miners that solved it received 6.25 BTC. In the case of Bitcoin, currently that's 6.25 BTC every 10 minutes being awarded to the miners. If a block is solved faster or slower than 10 minutes, the difficulty required is adjusted up or down accordingly to maintain a 10-minute block time. With Bitcoin, this adjustment only happens once every 2016 blocks, but other cryptocurrencies may adjust the difficulty much more often. So now the fun part. Let's actually take a look at an example. I mean, this is going to be super simple and just kind of hopefully make it all make sense, kind of put everything together, make sense of what's going on whenever you're talking about a block being solved and hashing functions and all that stuff. So that's what we're going to do now, just a quick little exercise and example of what is actually happening on a much slower pace than what is actually happening, and we'll talk about that. All right, so let's have a little bit of fun here. We are going to simulate a mining operation, a hash function, to try to determine the hash output, the digest, that is below the target difficulty of a block. All right, so this guy's got this cool little tool here created, Greg Walker. Yeah, I found this just poking around, and it seems like it's a pretty good little tool to show the examples of how the hashing functions work and what they're actually doing behind the scenes. So let's start filling this out. So if we take the hash from the previous block, let's go over here to just a block explorer. We're going to say, I'm going to take this hash right here, plug that in over here. The Merkle root, which is just a digest of all the transactions in a block. They're all hashed together. That's what the Merkle root is. So we're going to grab that from over here just so that we get the right number of characters and all that stuff. Just simple way of doing it. Copying and pasting here. The time, the format looks like that. We can go and grab that from over here too, I believe. Right here is a good example. Doesn't really matter because we're just trying to simulate the hashing functions of what happens. Paste that in there. The bits is the difficulty. They've got it shown here as 8 digits, I believe. Through some conversion, I think it actually ends up being, a regular integer. But I think that what we'll probably have to do for this is just simply put in some numbers here. Let's just do just to simulate the difficulty level. I don't know. We'll see once we run the hash on it to see what it shows down here as far as the target. Let's see what that shows. The nonce is the number only used once, and that is provided by the network, but I believe that you can actually set your own. I don't know if you have to use that for the beginning part of your hashing function, but basically it's a number that's only used once in your hashing function or your hashing communication. All right, so once we get all that in there, so this is basically think of this as the input for the new block of transactions, which is represented by the Merkle root here. So that's the new block of transactions. The previous block is here. So that's how you create the blockchain, right? If you're able to add this block, this information to the blockchain and string these blocks together, then that's where you get your blockchain from. I did see a version over here too. I guess you could put whatever you wanted in here. I don't know where the version number is actually pulled from, but we'll just make it look similar. All right, and then whenever you click the hash button here, that is basically your computer simulating your computer, your miner running a single execution of the SHA, in this case SHA-256 hashing algorithm on the data that you're being presented with here. So the input data hash function ran on it, output data. And this is just a single time. So I'm going to click hash. And you see that the target, based on what we put in the bits here, has like 3, 6, 9, 12 leading zeros. And the results that we had were not below the target. See, it says fail down here. Now, I'm not going to sit here and try to get below the target because that would be very, very, very difficult. That's a single function. Now, if you just run the hash again, you're going to get the same information because the input is the same. And remember, this is a one-way hash that if the data doesn't change, the output will always be the same. So if you just keep clicking hash, you're just going to end up with the same exact output, right? Because the data hasn't changed. So you might be wondering, okay, so how do we get the data to change? That's where the nonce comes in. You actually increase, I think that miners are set up to increase by a random number basically, but over and over and over to change the hash output. So in this case, we would just change the 3 to a 4, for example. And then if you look down here, watch this number down here, the block hash. Whenever I click hash, it's going to change. The whole number changed all together just by changing one digit, one bit of information up here, changed the entire block hash. So you can see how this works. So if we just kept going, this is what your computer is doing, your miner is doing whenever it's trying to find a result, an output, a digest of the information that is below the difficulty target. So the more zeros here, the more leading zeros, the more difficult it will be to find a random hash based on the nonce that you're plugging in here that would be below that target. Okay, so you can see, I mean, we could sit here, imagine this, because this is literally one per second, for example. Okay, so this is basically 1 per second. Now think of that mega hash, millions of times per second that this is happening. And that's how eventually you will come up with a solution, hopefully faster than any other miner on the network. You're going to come up with a solution that is below the target difficulty. So hopefully that makes sense. This is happening, I mean, I'm doing this super slow, obviously, but you know, it's happening millions of times a second in your computer or in your mining rig. So just to reiterate and summarize here, all of the input data here, we are running that through the SHA-256 hashing algorithm, getting a digest, an output, and we're looking for the block hash to be below this target right here. So we would need to have a leading 8 zeros down here on the result. So that's why you just have to keep going through this. This is what's happening on your miner a million times per second, many millions of times per second. And they're just searching for, they're modifying the nonce and they're searching for a target or a block hash result that is less than the target difficulty. Let's break down the hashing process even further just to show you how we get to the point of having an input for the hashing algorithm to use. So the first thing that happens when a block of transactions are discovered on the network, that block of transactions is hashed. So we're going to take an example here. We're going to say that we've got the first transaction. We'll use Bitcoin as an example. So just for example here, we've got the first transaction. We're going to go to a SHA-256 hash generator. The first transaction looks like this, sending 0.5 BTC from this address to that address. We're going to generate a SHA-256 digest. So this is the output. And remember, you can't go from this output and determine what this is. It's a one-way hashing function. You could, but it's would take you a phenomenally long time to solve that way. So it's a one-way hashing function. So now we go and we're going to document that hash for that first transaction. Our transaction example here, or our block example here, only has 3 transactions just to make it simple here. So that's the first transaction. That's the hash of the first transaction. So now we'll go with the second transaction. It looks like this. 1.34 BTC. And we go generate. So now we have the hash from the second transaction. We're going to document that. Then we'll go with our third transaction. This is a whopping 75 BTC transaction here. We're going to go generate. Now we have our SHA-256 hash digest from that transaction information. I'll throw that in here. So now we need to get the Merkle root, which is basically all of these transactions hashed together, right? I know this is super simple the way I'm doing this. It's far more complicated than this, but I'm just trying to give you an example and help you understand what's going on here. We're just going to throw all these in here. Again, this is just a super simple example. Then we're going to generate, and now we have our, actually, you know what? I don't even think we have to generate. I think it does it for us. Yeah. So now we have our Merkle root. So we're going to copy that to the clipboard, paste it over here, because that's what's actually used by the miner. This is like the previous, or this is the current block hash information right here. Then we have the nonce, the number only used once. We can just grab, I mean, it's a random number, so we'll just grab an example here. So the nonce is that right there. And then the network has provided us with the current difficulty target, which is right here. So hashing all this stuff together, we need to come up with a number that is below this target. And you can see how difficult that might be because, you know, I mean, we've got 19, I think, leading zeros here. So just hashing randomly all this information would be really difficult to come up with a number that's below that target. So the first thing that happens is the hash of the contents of the new block is taken. The nonce is appended to the hash. Okay, so here's where we get into what's going on your miner. So we're going to copy that Merkle root, paste that in here. Then the nonce is what is added to or appended to that Merkle root, like that. Okay, and you can see how, if you watch down here, you can see that the hash is changing, right? The 3 doesn't really matter, but yeah, 3. Okay, so that's what your miner is doing, is looking at this number and running that through the hashing functions. Okay, so this should explain, well, okay, if the hash is the same for the list of transactions, for the block of transactions for everybody, then how do we arrive with a random hash? And that's the function of the nonce. The nonce is what is changing each attempt at hashing this algorithm and coming up with a target that is below this. So if you're thinking about what's going on here, you know, if you change one digit, the whole number is going to change, right? So you saw that in here. If we change that, watch this number down here, the output, watch the digest. So if we change this to a 4, that number down there is going to be totally different, right? So think of this millions of times a second happening where that nonce is changing, right? It's cycling through all the different nonces. It's not affecting the data. The hash of the actual transactions is still the same, right? And it knows how long the nonce is. So it's not affecting the data. You're only changing the end of it. The concatenated end, the appended end of this is the nonce. And that's what's adjusted to try to make another attempt at solving the block. of transactions and getting that output to be below that target. So each time the nonce is changed, that new string is hashed, then that final hash is compared to the difficulty level, like I was just saying, and down here, and if it sees whether or not it's less than that number or not. If not, then the nonce is changed and that process repeats again. If the target is below, or if the resulting hash is below that difficulty target, then that means you win and you're going to receive the reward for adding that block to the blockchain. So all right guys, clear as mud. Hopefully this at least gives a little bit of information and at least helps you understand what is going on whenever we're talking about hashing and mining, and why we would receive some rewards for doing all this mathematics, all this what they call it, a complex mathematical equation, which you can see that it is not. It is literally a hash function applied to a set of data, and then the output is compared to the current difficulty target, and that's it. That's all it is. So it's not a complex mathematical equation. All right, guys, that's going to do it for me. I will see you guys next time. Stay savage, everybody.